Hello everyone, this is Shashank Sekhar Singh from Target Academy, and you guys are welcome to the second episode of the mock interview training. Here we have with us Harsha Sharma, mechanical engineering graduate from Johar Institute of Science and Technology. Hello Harsha, good evening. Am I audible to you?
Yes, sir. Good evening. You are clearly audible.
Okay. According to the previous episode in which I took an interview of yours, I think there were a lot of lessons to learn from it, isn't it?
Yes, yes, sir.
Okay, so basically in this particular episode, I'll be asking you more and more questions from the core mechanical subjects, and let's see how much preparation have you done. And definitely, if you want to write something and explain, also you can share the screen without any problem. All right.
Okay, sir.
So yes, basically, since you will be appearing in the engineering sciences paper of GATE 2025, so I think like there is a subject called fluid mechanics out there, isn't right?
Yes, yes, sir. Yes,
So in the fluid mechanics, it's a huge topic, huge topic, and
yes,
it's a very conceptual topic as well, right? So
yes, sir.
let's start with this. And okay, fine. Talking about fluid mechanics, what are the different properties of fluids that we consider while we analyze the fluid motion or the static condition of the fluid? What are the different properties of fluid that we consider into?
So, dealing with different like topics of fluid mechanics,
Hmm.
like example, fluid kinematics, fluid statics,
Hmm.
we analyze we see different properties of fluids.
Uh,
For example, we talk about the viscosity,
yeah, very
which
nice.
plays an important role,
Uh,
and moreover, the pressure and temperature associated with the fluid, because it will also affect the viscosity in one or
Definitely.
another way.
Very good.
So
Very good.
mainly we observe the mainly our deal is to tackle the friction losses that are involving in the fluid, and mainly reduce it, which comes because of the viscosity.
Okay, okay. So isn't there any other properties that you are thinking of as of now, fluid properties? When we kindly stress a bit, like you will come up with certain different
Okay.
properties as well.
Okay. Like
Something
like
okay, something like specific gravity and
yeah. Specific gravity. Okay. Specific
specific
gravity,
gravity is
relative
there.
density.
Then
Okay.
specific weight is there, right?
Yeah. Specific. Yeah.
Uh,
Specific gravity, relative
Yeah,
density.
yeah. Relative density. Relative density is not
Yeah.
just a property. It's a relative thing of like it's
Yeah.
a relation
Yeah.
between two different densities of a fluid
Yeah.
when we consider.
Like all specific gravity are relative density, but
Uh,
vice versa is not.
Not, yeah, very nice. So specific gravity, when we talk about specific gravity, so we compare something with something, right? It is a ratio of
Yeah.
something. Can you tell me what is
Yeah.
the
Yeah.
ratio about?
Okay, specific gravity is density of fluid one, so
Uh,
any fluid we are taking,
uh,
divided by the reference density.
okay.
If it is water, then the reference density will be 1000 kg per meter cube.
Yep.
If it is air, the reference density will be 1.23 kg per meter cube.
All right.
But in terms of specific gravity, this is specific gravity. But in terms of relative density, it is simply density of one substance with respect to
So
density of the other substance.
right. So basically, when you talk about specific gravity, there is a small correction out here, Harsha. Okay. So when we
Yeah,
talk about specific gravity, the original ratio is about the specific weight of one liquid, yeah, one fluid,
yeah,
compared
yeah,
to the specific weight of the standard fluid.
yeah,
The standard fluid,
yeah,
generally we take water at thousand water the at 4 degrees Celsius, at which the density of water comes out to be 1000 kg per meter cube, right?
yeah.
Right. So there is another property that also will deal with the liquids basically, and that comes up as surface tension. You heard about surface tension?
Yeah, not much, but yeah, I have heard.
Okay,
I have
okay,
heard.
fine. There is a question in surface tension. Okay, there is a conceptual question. I'll ask you. I want to see whether you can answer or not. So when we talk about surface tension, does surface tension depends on only one fluid, or it depends on two fluids taken at a time?
It will depend on two fluid taken at a time, I think, because for one fluid, the force of attraction will be on same molecule. But
Uh,
for surface tension phenomenon to occur, we need
uh,
adhesion between the fluid particles. That is
yes.
force of attraction between different fluid
Oh,
molecules.
yes, right. Very good. So basically, surface tension appears it does not appear on the volume, it appears at the surface, right? So it acts at the
Yeah,
surface. So basically,
yeah,
if you consider surface tension of water and some other, other thing, then water and air will be different, and water and glass will be
Yeah.
different. So it
Yeah.
depends on the material to material, which the liquid is.
Okay.
This is one important question, Harsha, because many a times you will be asked question on surface tension, and they will try to like bend it to their way.
Yeah.
All right.
Yeah. Yeah.
So now, when we talk about surface, like we have talked about surface tension and everything, and now the most important part of fluid mechanics is the measurement of the pressure of a fluid, right? So,
Yeah.
so in case of measurement of pressure, so we study about one topic which is known as manometry, isn't it?
Yeah. Yeah.
All
Yes, sir.
right. So, what is the main drawback of simple YouTube manometer, or we can say, what is the main drawback of piezometer?
Uh, Sir, in this pressure like piezometer
Hmm.
or like simple YouTube manometer,
Hmm.
very low pressure can't be measured accurately.
Okay.
That's one of the drawbacks.
Now I'm talking if I'm talking about piezometer, you have to stand correct with the piezometer thing. Like I'm talking about piezometer.
I think piezometer measures only static pressure.
Yeah, manometer also static pressure only. Otherwise, all these manometers and everything is like static pressure
Like,
only.
or, like this is the I can think of
Oh
on
yeah.
heart.
See, okay, I'll make you. I'll definitely throw some light on it. When we talk about manometer, so we use a specific kind of a fluid which is known as manometric fluid. In most of the
Yeah,
cases, we
yeah,
use
yeah.
mercury, right?
Mercury. Yeah,
In case of piezometer, it's just a simple tube attached to the center of the pipe, right? So there is
yeah,
no manometric fluid. So from piezometer
yeah.
point of view, we cannot measure the static pressure of a gas. We can measure only liquids.
Oh, yeah. Yes.
Because in
Yeah.
case of gas, the gas will flow out to the atmosphere automatically. So
Okay.
it will never
Okay.
form a surface with the atmosphere, right? So we'll never know at
Okay.
what point is the liquid column is, at what point the column of the gas is. So we cannot know. But in case of manometer, if we provide manometric fluid, then definitely the pressure of the gases can also be measured because manometric fluid is heavier, and on the other side, two limbs are there, right? So yes, this is one of the questions from pressure measurement. Pressure measurement in fluid is governed by one of the laws. Can you tell me what is the law that we talk about?
Okay. It is basically Pascal's law.
Yeah, very good. And what does it state? Pascal's law.
The pressure at a point
Hmm.
uh, in fluid the pressure at a point is same in all the direction.
Oh, very nice, very nice. And there is another law which governs the measurement of pressure, which plays a crucial role in hydrostatic forces of surfaces. What is that?
In measurement of pressure.
Yeah, in measurement of pressure, we study about that particular law, and that law is also applied in hydrostatic forces on surfaces. So, what is that law?
Okay, Bernoulli's law
No, no, no,
for
no.
static fluid.
Bernoulli's law is not for like statics
Like
condition. Yeah, it's like
like I can like derive Bernoulli's equation and get the velocity term zero. Then I can get P equal to rho g h from
okay,
which I can like use like these equations.
okay. So that was not my point, Harsha. The point was that there is another law which governs with the pressure and the measurement of pressure with depth and everything. So that is hydrostatic law, as you can
Okay, okay, okay.
okay. That is the rate of change of pressure with respect to depth of the liquid is equal to the
Yeah, yeah,
specific weight of the
yeah,
liquid,
yeah,
right?
yeah,
And this law you cannot forget because this law is something which is applied directly into manometry
yeah,
and as well as also directly into the measurement of
yeah,
forces in hydrostatic conditions, right? So yeah, fine, sure.
yeah.
So this is one another thing. Moving on to another topic, which is fluid motion, fluid kinetics. So under fluid kinetics conditions, we study about two different topics. One is fluid kinematics and fluid dynamics, right?
Yeah.
So what is the basic difference between kinematics and dynamics?
In kinematics, we learn about the motion without knowing its cause. In
Okay,
dynamics, we mainly deal with the cause that is causing the motion.
yeah,
Like mainly deals with the force and
forces,
the
yeah.
yeah.
So the same thing reference is drawn back to the viscosity part. So there are two types of viscosity that we talk about. What are those?
Yeah. One is dynamic and one is kinematic viscosity.
Okay, fine. So what is the SI unit of dynamic viscosity?
Like I can prove it like but I don't because I don't remember like
Uh,
but I can prove it from
uh,
simple
from
Newton law of viscosity I
this
can
kind
prove
of
it.
viscosity. It is Newton second per meter square, right? So
Yeah,
And
yeah, yeah.
and what is the CGS? What is the name of the CGS unit of dynamic viscosity?
I think poise.
Poise, very good. And there is a relation between poise and SI unit. What is how much one poise is
Yeah,
equal to?
10 to the power minus 1 meter
Yeah,
per
very
second.
good. It is 0.1 Newton second per meter square. Right? Very nice. And moving on to kinematics and dynamics. So, why when we talk about the different concept that we talk about in case of studying the fluid mechanics, yeah, fluid kinetics, there are two different concepts that we talk about. What are those
Yeah.
concepts that we
Okay. Okay. We basically deal with Lagrangian and Eulerian approach.
very good, good
But in fluid mechanics, we deal with control volume approach, which is mostly Eulerian approach.
approach?
We don't deal with Lagrangian
Uh,
approach much. It
correct.
is for like topics like engineering mechanics where we are dealing with single particle.
Particle. Okay.
Here we,
Okay, nice. So Lagrangian concept is about the molecular thing, and it's about
yeah,
the something called when you talk about Lagrangian concept, it is broken down into the molecular part and consider one fluid particle study and analysis of one fluid
yeah,
particle. Very
yeah,
nice, very nice. And when we talk about dynamics, so what is the major purpose of using venturimeter?
okay. Venturimeter is mainly used to measure discharge.
Okay, nice.
Discharge. Yeah.
Okay. So discharge as in like what would call as a discharge? Like what is discharge?
The mid- the the discharge is nothing but volume flow rate per second.
Oh, one
I mean volume flow rate.
follow it.
I
Very
don't
good.
say per second.
Yeah,
That is five.
yeah.
So it is okay. The discharge can be measured with the in terms of piezometric health.
Oh, okay. Nice. Good. So
Yeah.
basically, it establishes a relation. Bernoulli's principle is based on one of the basic laws of is this universe. What is that law that we talk about?
Energy conservation
And
basically.
basically, energy conservation and mass conservation both, right? So
Yeah.
yes,
Yeah.
so mass and energy conservation, these are the two. And then later on, we
Yeah.
also talk about one of the most important conservation principle, which is known as momentum conservation principle. So three principles will
Yeah.
govern.
Yeah.
See, there is a question that will be asked to you, that might be asked to you. There are three principles in fluid mechanics that governs the entire analysis. What are
Yeah.
those three principles? So you will have to say that your conservation of mass, conservation of energy, and conservation of
And
momentum. All these three.
yeah. Yeah.
So when we talk about fluid dynamics, so venturimeter is there. There are another devices like orifice meter. So while using Bernoulli's equation, while applying Bernoulli's equation to all these devices, there are few assumptions in Bernoulli's equation.
Yeah.
Can we
Yeah.
use this Bernoulli equation in turbulent flow?
Uh, as far as the fluid is incompressible
Uh,
and it is going through steady state
hmm,
and fluid is invisible, we can use Bernoulli's equation, no problem. Anywhere we
Bernoulli's.
can use.
Anyway, we can use, yeah.
As
So
as the okay,
okay,
yeah.
tell me. You continue. What?
I mean, if it is not violating these three laws, we
Hmm,
can use Bernoulli's equation.
hmm,
But there are some parts where we strictly can't use Bernoulli's equation.
hmm,
For example, inside for example inside boundary layer.
oh,
Inside boundary layer, what happens is that there is velocity gradient.
hmm,
So there are viscous effect present. So the
yes.
fluid is now rotational.
Rotation.
So we cannot use Bernoulli's equation. But
Yeah.
outside the boundary layer, we will be able to use Bernoulli's equation. So
Bernoulli's
these are
equation.
some of the limitations.
So, yeah, some of the limitations. So, basically, again, I'll stand you corrected. Whenever we talk about Bernoulli's equation, the primary assumption in Bernoulli's equation is that the fluid is laminar.
Yeah,
That we talk about, the fluid is
obviously.
laminar. And when we talk about turbulent fluid flow, the analysis is completely different. It's like
Yeah,
completely different in case of turbulent flow. So
yeah,
if you
yeah,
talk about head losses in turbulent flow, you will not be able to use Bernoulli's equation or
yeah,
anything out there. You have
yeah,
to use different approach out there.
yeah, yeah.
All right. So when we talk about fluid motion, can you tell me the difference between steady flow and uniform flow?
Okay, in steady flow, the fluid properties and flow velocity
Hmm.
do not change with respect to time at a given location.
Okay. Nice.
For example, suppose fluid is flowing in a nozzle.
Hmm.
Suppose at I am taking 3 points, one,
Hmm.
2, 3,
Hmm.
and I'm watching at 1 p.m.
Hmm.
The velocities are 1, 2, and 3 meter per second respectively.
Hmm.
At 2 p.m. also it will be same 1, 2, and 3 meter per second respectively. So basically, velocity is not a function of time, but it is a function of space.
Space. Very good.
In yeah. So
Okay.
in uniform flow, what happens is the fluid velocity and flow property
Hmm.
do not change with respect to space. Suppose again, if I'm taking like pipe, and suppose I'm watching at 1 p.m., the velocity will be 1 meter, 1 meter, 1 meter. If I'm watching at 2 p.m., the velocity will be 2 meter per second, 2 meter per second, 2 meter per
Hmm.
second. There won't be any difference.
Hmm.
So
Hmm.
this is so here it is a not function of space, but it is a function of time in
Okay.
uniform flow.
Uniform flow.
In uniform
You have told the opposite thing.
flow, no, no. In uniform flow, velocity is not a function of space. It is a function of time.
Uniform
In
flow.
steady flow, yeah, in
Okay.
steady flow, velocity is a function of space, but it is not a function of time because d of something by dt will be zero in
Zero.
steady flow.
A steady flow. So in steady flow, velocity does not change with time. Okay, at different
Yeah,
locations.
yeah,
In
but it will
steady,
change with space.
it will change with the space. Yeah. So
Yeah,
it is a function of space. Yeah, fine. And uniform flow we talk about is that like at different conditions of different spaces, different locations of a fluid flow,
yeah,
the velocity
yeah,
and flow properties will be same throughout completely. So that is
yeah,
uniform
yeah,
flow.
yeah, yeah, yeah.
Fine. Uh, and what is the difference between instantaneous acceleration and total acceleration in a fluid flow?
Okay. Total acceleration is the sum of convective and local acceleration,
Yeah,
and instantaneous acceleration is nothing but the acceleration of the point where we draw the tangent
yeah,
with when we are analyzing the point. It is basically dv by dt,
dV by dt.
and it is convective plus local
Okay.
acceleration, the total
External,
acceleration which we
external.
talk about.
So it is a differential form. Basically, instantaneous is a
Yeah,
differential form, and we break it
yeah,
down to the very smallest part. And that particular
yeah,
instant, we okay, fine. That is dV by
yeah.
dt. Nice. Okay. So how good are you with strength of materials, Harsha?
I haven't revised much. I was like doing before, like when I before I was not sure that I will be preparing for ME or XE.
Okay.
After I decided that I'll be mainly focusing on XE, then I stopped studying other subjects. But
Okay.
yeah, I
All right. So in terms of some, anyways, like see, when you are appearing in Axis, so you never know what kind of paper fluid mechanics will have or what will have SOM. In my
yeah,
opinion, is
yeah,
that like if you consider SOM is a bit easier one,
yeah.
then I would suggest you try the SOM part basically. So
Okay.
in my
Yeah,
opinion, if you are going for Axis paper, so I would suggest
yeah,
you carry forward thermodynamics, SOM, and fluid mechanics together. Okay, you study
yeah,
SOM also
yeah,
because you never know the
yeah,
level of toughness from fluid mechanics or
yeah,
SOM. So if you find SOM
yeah,
easier, you can appear in that also, no problem in that.
yeah.
So talking about SOM, strength of material, that is a very interesting topic, and there is one type of stress which is known as principal stress.
Yeah.
Yeah. So what is principal stress in your opinion?
Okay. A principal stress is the stress which will be acting on the principal plane,
Hmm.
and and it is the maximum stress acting at that point and acting at that plane where the shear stresses are zero.
Okay, shear stresses are zero. So principal stresses. Okay, fine. So you cannot say that principal stresses are the maximum because sometimes you have minor principal stress also and major principal
Yeah,
stress.
yeah, minor and
I
major.
mean,
I'm talking on magnitude wise
yeah,
now.
magnitude wise. So if you talk
Yeah,
about if you are given certain condition of sigma x and sigma y along with tau, then you will have
mm,
to whenever you are asked about principal stress, so you will say that principal stress is a normal stress. Always remember, it is a
yeah,
normal
yeah, yeah,
stress.
yeah. Okay.
It acts
Yeah,
perpendicular to the plane, and that plane does
yeah,
not carry any kind of shear stresses. That is principal
yeah,
stress. Fine.
yeah, yeah,
All right. So principal stress goes into a lot of consideration, and principal stress is utilized in machine design as well, right? Later on,
yeah,
in
yeah,
order
yeah.
to find whether there is any failure or not. Fine.
Yeah.
So basically, when we talk about strength of material and simple stress and strain, there is one kind of stress that we generally deal with, and it is very common in today's life or in common in engineering basically. That is known as thermal
Mm,
stress, right?
yeah, yeah,
So if the temperature is increased in a structural member, if the
yeah.
temperature is increased in a structural member, what kind of stress will be induced in the material in the member? It will be tensile or compressive.
In a structural member, if temperature is increased.
Yeah. So what kind of stress will be induced? Thermal stresses will be induced, so it will be tensile or compressive.
Okay, if it is freely expanded,
Uh,
then there will be no stress because
very
stress
good.
is resistance force per unit area.
So,
If it is like freely suspended and we are heating, then no
uh,
stress will develop. There
there.
will be strains, but there won't be stress.
Uh,
But if it is not like free, the end is not free.
uh,
It's like joined.
hmm.
Then depending on the behavior, it will change. Like it can be compressive, it can be tensile.
I
Like
think so.
usually, no, actually, there I made a mistake. Usually, it will try to
Uh,
expand, but the fixed support may try to compress it. The bar will try to expand.
uh,
Then the stresses will be developed, but the fixed support, it will if it is touching the free support,
hmm.
it will try to compress the bar. So
So there will
yeah,
be compressive stress in the bar, right? So it will
yeah,
never
yeah,
be
yeah,
tensile. So you see, understand one thing out here. Like, see, so this is, you can see this, right? So you can see
yeah.
this. Just a minute. So this is a structural member, and these are the supports. If you heat it, then definitely in this case the material is not going to yield anyway because it is not being allowed
Yeah,
from both the sides.
yeah.
So
Both are
it
fixed.
tries to elongate, but it is not being allowed. So whatever the strain would have been, whatever the amount of free expansion would have taken place in this case due to the increase in temperature, it is not being allowed because because this particular supports is what holding it back.
But
So
due to Poisson effect, it will increase in diameter, I think.
diameter, yeah. So that will lateral thing, but in this case,
Yeah,
this
it
material will
won't.
always be in the form of in the state of compressive state. Okay, and if you reduce the temperature of this structural member, it will try to shrink, but but this fixed supports will pull it apart. It will not let it shrink. So in case of
Yeah,
temperature decrease or cooling effect,
yeah,
the particular structural member will suffer from, yeah, it will have tensile stresses induced in it. Fine.
yeah.
All
Like
right.
L
So
alpha delta, L
yeah,
alpha delta T.
130. Yeah, very good. And also one thing, stress is a scalar quantity or vector quantity.
It is a tensor. It is a
Ah,
second. It is a second order tensor.
yeah,
I said. Yeah.
it is a tensor quantity. What do you understand by tensor quantity? What to
It
explain by?
has magnitude, direction, and also a plane.
Yeah, very nice, very nice. So it also includes the plane on which it is acting, right? Fine.
Like,
So
like for example, like for examples, I think scalar quantities that we have only magnitude.
uh,
These are zero order tensor.
yeah,
Zero order tensor.
uh,
Vector quantity. These have magnitude and direction. These are first order tensor.
tensor. Yeah, very
Stress,
good.
they have magnitude, direction, and plane. These
Plane
are third. These are second order tensor
tensor.
quantity. Zero
Yes,
order, first order, and second order
exactly.
tensor.
Very nice. Very nice. So we represent this. This represent this stress thing, three-dimensional stress or two-dimensional stress. We can represent in
Yeah,
a matrix form, right?
yeah,
So,
yeah.
do you have any idea about that matrix form? How to write down or something?
Okay, I can write it down. Like first, I'm just talking about the first column.
Huh?
Like it will come sigma xx plus uh, tau xy plus
Yeah.
sigma xy.
No,
Oh,
tau xy and tau xz. Uh,
okay, x. Okay,
can you
x
write?
explained.
Can you share the screen and write down? Can you, if you have the possibility here?
Okay, I will try. Like I remember correctly.
No problem. Just if there is any problem, I'll correct it. Right? No problem. Sharing the screen.
Okay, is it visible?
Yeah, visible, visible.
Okay, 1 second. Am I audible?
Yeah, yeah, you're audible. No problem. Go ahead.
Okay. Uh, okay, like sigma xx.
Yeah, very
Uh,
nice.
Is it correct, the first
No,
column?
it's no. You can't. No.
Okay. So I have like
Basically, this will be you write down the first. What I am saying, you write down. This is tau xy, right? Second thing. Second thing you have written is tau xy.
this
Okay.
is sigma z. This is right.
No. See, all yeah, making a mistake out here.
And
I'll show you one thing, right? See, because this is
I
something.
forgot.
It's okay. It's
To
okay. No
remember.
problem. No problem, Harsha. It's there. Still, there is a time because if you're preparing for examination of national importance, then definitely you will have to, prepare from now onwards in such a way that you do not make mistakes later. Making mistakes now is not a problem, but making mistakes later is
Yeah.
a problem, right? Yeah. Okay, I'll show you, Harsha. I will show you. Can I share the screen with you once?
Yes, sure.
Just a,
I forgot the expression.
no problem. No problem. Just a minute. So I guess you can see this. Just a minute. I'll share the screen with you. You put this. You can close the screen share from your side. No problem. Right? Can you see the screen, Harsha?
Yeah.
Okay.
My screen share is closed, I
Yeah,
think.
yeah, it's okay. Can you share my? Can you see the screen on from my side?
Yeah, yeah, I can see.
All right. So basically, when we write down stress, so stress is given in case of this. Always remember the direct stresses are always in a diagonal of the matrix: sigma xx,
Yeah, yeah,
sigma
yeah.
yy,
Sigma
and
mobile.
and sigma
My
zz.
God.
And this row will represent x plane. Okay?
Yeah,
This row will represent plane, so this will be y plane, and this will represent the z plane. So always remember the first subscript sigma ab we are writing down. This is representing the plane, and this is representing the direction. Always remember. All right.
hmm.
So in this case, tau xy, it is acting on x plane in y direction. It is tau
Yeah,
x plane z direction. So this will
yeah, yeah,
represent directions. This is x direction,
yeah.
y direction, and z direction.
And the second one will plane.
It will be tau yx, all right, and
Yeah,
y plane x direction, then y plane z direction, then again it will become
yeah,
z plane x direction, z plane y direction. Is it clear? All right.
yes.
And these two will always be complementary shear stresses. These two are complementary shear stresses, and these two
These
are
are
always
same value.
yeah, same value. If you apply
Yeah,
one shear stress on one plane, automatically the other
yeah,
will start developing,
yeah,
because it has to
yeah,
counter it back to the original shape. Because there is, whenever you apply shear, then there is a case of, you know what, like there is a case of distortion in case of in the
yeah,
material. So in order to prevent the distortion for a permanent thing, opposite side से complementary shear stress लग जाता है आराम
yeah,
से.
yeah,
So yeah, basically I can see that strength of material needs a bit of brushing from your side, because
yeah, yeah,
it's a small
yeah.
amount. So I will suggest that if you take my advice, Harsha, from here, okay, if you are
Hmm.
preparing for thermodynamics and fluid mechanics, at the
Yeah,
after this puja thing, after this puja vacation and all, okay, you can
yeah,
go for, you can brush up your strength of material part as well. I would
yeah,
suggest appear in
yeah.
tests. There are tests available in Target Academy. You can apply for free and all. Okay, so you can appear in the
Okay,
test for
okay,
this,
okay,
and
okay,
when you appear in the test, you get the confidence built up. All right.
okay.
Okay, and also one thing in XC, you guys, you have to study about turbo machinery also, hydraulic machines.
No, no, not only thermal application part, not
Oh,
fluid application.
not for application part.
But extra fluid topics we need to study like Navier-Stokes and its exact solutions, like
Solutions.
Hagen-Poiseuille, Plain-Poiseuille, and thin film fluid.
Yeah, yeah, fine, nice. And there is one more thing that I wanted to ask you today. Like I prepared this sort of this list of questions for you. There is one there is one equation that we use that is known as Darcy-Weisbach equation, right? Darcy's law.
Yes.
What
Yeah, yeah.
what does it why is it used for? What do we do with the Darcy equation?
Okay, it is used to calculate frictional head loss.
Yeah.
HL equal to FL square by 2GD, where F is the
Oh,
friction factor.
very good, very good, nice. So this is applied in which concept? Where do we use it? Darcy-Weisbach equation.
It flow through pipes basically.
Flow through pipes. Nice, nice,
Both
nice.
laminar and turbulent we can use it. But
Yes.
for laminar, the FLB square by 2GD terms will change. For example, 32 mu VL by rho
Ah,
GD square,
well,
or 120 mu QL by pi GD to the power 4.
okay, nice, very good. So that is thing. Yeah, you guys, you are good with the formula part and then application part. Yeah, understand. And
Yeah.
from fluid mechanics, I don't think like there is much to ask. And one more thing I'll suggest you here, Harsha, that look into the dive into the smaller topics. Like every Saturday, you can go through the topics like
Uh,
the types of fluids we study about, like Newtonian fluid, non-Newtonian fluid. What are
no,
the
the
different?
rheology I have covered.
Yeah.
Rheology and boundary layer theorems I
Okay.
have covered.
Nice. 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 So basically,
Yeah.
the questions whenever we talk about interview questions, the interview questions are not very, like it's not very application oriented. It's just about the basic oriented. So people will ask you
Yeah.
questions from the basic part, whether or not
Yeah.
like you like it or not. But it's the thing,
Yeah.
because
Yeah.
in some of the interviews of PSUs and some of the interviews, they might give you an opportunity to write on the whiteboard if it is there,
Yeah.
if it is available. Like
Yeah.
in
Yeah.
case of ISRO, they conduct
Yeah.
the interview in presence of a whiteboard so that you can explain something to them, right?
Yeah. Yeah.
All right. So, okay, Harsha, this will be the conclusion of the interview here. And in,
Yeah.
you prepare for some time, okay? And in the next month,
Okay.
again, we will meet for once and then we will see them. Okay. Thank you so much
Okay.
for
Sure.
coming, Harsha. I'll see you the next time.
Thank you.
Right. Best wishes for the
Okay.
preparation.
Thank you so much.
Okay,
Okay.
sure. So this was the end of the interview part. I hope you guys liked it. And after this, basically, if you are watching this interview, and always remember while you are watching a interview video, so remember that you whether you test it, you gauge it, like whether you are able to answer the questions by yourself or not. If you are not in a state to answer the questions like this, these are the basic things. So I think you guys need to put in the hard work or the smart work from now on, so that you do not miss out on the basic concepts. And this basic concepts will be required in any kind of competitive examinations across India, be it the PSUs, All India Limited, or anything. You just go and flip through the pages of the previous year's question paper of any competitive examinations, recruiting, mechanical and civil or whatever. You will face these kind of questions for sure. And interview questions also, these are interview questions are something which is required, where you need to answer the questions from the very basic part, like the SI units, the CGS units, why do we name it as something like that, where do we use it, and what is the primary reason of why we are using it. So they will just ask you the basic parts. Like, so in whenever you are preparing for any subject in your semester, always remember three things, three W's. Is like what, why, and where. What is this concept? What is this concept? Second thing, why we are using this concept. And third thing is where we will use this concept. Apart from this, if you are not able, if you do not get answer of these questions for any kind of concept, feel free to contact the Target Academy. I shall always be there to help you out in any case of, in any circumstances. Thank you for coming for the live for this video, and stay tuned for the next episode, that is episode 3, and see you in the next time. Thank you guys.